Hey everyone, welcome back to Calculus 3. This will be lecture 21 of the course. And in this lecture, we're going to expand on the results of lecture 20, where we talked about iterated integrals. And we're going to formally introduce the double integral and talk about how to solve volume problems using the double integral. All right, so let's go ahead and jump into it. So we'll call this section 4.2, double integrals and volume. Okay, so base kind of wind up here. We saw previously, obviously, that we can use this idea of a definite integral on an interval, so specifically referring to functions of a single variable. We can use a definite integral, evaluated on an interval alongside we've seen that the definite integral uses a limit process to assign some measure to quantities such as area, volume, arc length, etc. So what we want to do is kind of, in the spirit of those initial constructions of the definite integral, we want to set up a similar kind of construction to define the double integral of a function of two variables. Okay, so hopefully a lot of this argument will be, not exactly the same, but similar to what we saw in Calculus 2. So we want to use a similar construction / argument to define a double integral. Okay, and when I say similar to the argument we saw in Calculus 1, in Calculus 2. Right, specifically when we talked about finding the area of a region using an integral. Okay, now we want to talk about finding the volume of an area using a double integral. Okay, so to that end, let's go ahead and define some things. So we're going to be talking about a function. So we want to consider a function f of xy, right? And specifically, we're going to make this function be non-negative. Okay, so it's going to be non-negative for all xy defined, for all xy in some region we'll call R. Okay, and this region R is going to be on the xy plane. Okay, so basically we're going to have some, right, so here's our xyz plane. We're going to have some region in the xy plane. This is our y's, these are our x's, and up here's our z's. Some region of interest, and that region of interest is going to produce, a surface. Okay, it could look like this, for example. Okay. Our goal here, our goal is going to be to find the volume of the solid region. So we want to find the volume of the solid region that's going to lie between this surface and the xy plane. Okay, so this f of xy is going to give you, is going to tell you where you're at on the z-axis and where you're at on this surface, right? And so what we want to do is we want to be able to find the volume of the region. So we want to find the volume between the surface and the xy plane. So basically, if you think of this as a solid that comes down to the xy plane, right? It kind of looks like this. It's got some mass to it. we want to be able to find that volume. Okay, and so how are we going to do that? Well, how does the double integral accomplish this? Well, here's the idea. Okay, so what we're going to do is we're going to start with our region in the xy plane. Okay, and what we're going to do with the region is we're going to create a grid. Okay, this is not a very fine grid, but that's okay. It works for our illustration here. Okay, and our region of interest is going to intersect that grid somewhere, like so. Okay, and again, right, remember we've got this surface here, right, and then underneath it, in the domain of our function in the xy plane, we're going to create this grid. Okay, so we superimpose a rectangular grid on the region of interest, we'll say. Okay, and this grid is going to be in the xy plane. Okay, like so. And then the rectangles that lie within R are going to form a partition. Well, I'll say this grid. This grid will form a partition of the region R, right? And we'll denote the partition in the usual way. Okay. And this partition, we can define a norm on the partition, and we'll denote it in the same way as before. Define the norm to be the length of the longest diagonal of these rectangles. So we'll define the norm to be the length of the longest diagonal in the partition. Right, so I'm sure you can imagine what we've got in mind here, right? What we're going to do is we're going to start with a really chunky grid like this, and then we're going to use some kind of a limiting process to make the grid finer and finer and finer. And we just need some kind of a norm, some kind of an idea, some quantity that represents the fineness of the partition, right? And so what we've said is we'll just let the norm be the length of the longest diagonal in the partition, right? So, right, if you're looking down on your grid, then your norm is going to be this length for whichever diagonal happens to be the longest. That's what you're going to call the norm. Okay, perfect, right? So we've not done anything super crazy yet. All we've done is say, hey, we've got this region in space. We're interested in the volume between a surface and over this region. And to start with, let's just partition the region up into rectangles. Okay, so that's all we've done. And we've then said, okay, we can think of this grid as a partition, and we can define a norm of the partition to be the length of the longest diagonal of the rectangles. And how many rectangles will there be? Well, we'll say there'll be n rectangles. Okay, so what comes next? Well, what we want to do next is we're going to choose point xi, yi, okay, in the partition, and form a rectangular prism. We'll call it a prism. It's going to be prism-like. Okay, now what are we talking about here? Well, again, let's redraw the picture here. We've got our x, y, z axes. Inside there, we've got a grid that we have set up. Okay, we're going to grid this region off. Okay, now remember, so this is your x-axis, this is your y-axis, this is your z-axis. So this grid or partition lives in the xy plane. And remember, we're going to, there's a surface over all of this, right? Some three-dimensional surface that kind of comes out of the page here. Now what we're going to do is we're going to choose an xi, yi in the partition, right? So we'll just say like right here for, that's a bad example. No, that's fine. So we'll let that be our xi, yi. Okay, and then we're going to form a rectangular prism off of this point. Okay, and so you can imagine coming up out of this grid, you might have something like this. Okay, and so now what's happening here is this prism, add a little bit of shading so that you can kind of see what it's doing. It's coming up off of the grid, and where does it stop? Well, it stops on the surface, right? So it comes up through the surface, and the top of the prism is level with all of the edges of the surface. Okay. And so the point here will denote as xi, yi. That's the point. And what's the height of the prism? Well, and it's going to vary depending on which corner where inside the rectangle you are. But if we're talking about the height above xi, yi, the height is going to be f of xi, yi, right? That's going to tell you how high the surface is off of the xy plane. Okay. All right. And so let's denote the area of the rectangle as we'll denote the area of the rectangle as delta AI. Okay, that's a subscript. Delta A sub I. Okay. Right, and so if this is the area of the rectangle, then the volume of the prism, of this ith prism, right, the volume is going to be basically the base area, delta A sub I, times, and that's not the dot product, let me just write it like this, f of xi, yi, right? So it's basically the base area times the height. That's going to give you the volume of this prism. And that's the idea, right? So we could do this same, we could repeat this procedure for every point for every rectangle in the partition. We could add them all up, and when we do that, what we would arrive at is some estimate of the volume, right? So the volume is going to be approximately equal to the sum from I equals 1 up to n, however many there happen to be, of f of xi, yi times the area of the rectangle from the partition. Okay. And now, as we've seen, obviously, in previous integration constructions like this, the precision of this volume can be improved by essentially tightening the mesh of the underlying grid. So if the grid is a really fine partition, like very, very small squares, rectangles, then the precision will be high. If, however, in the other case, your grid is very chunky like this, then the precision will be very low. And what we can understand is that if we let the fineness of the partition increase without bound, or another way to say that would be to let the norm of the partitions decrease to 0, then the precision increases, and eventually in the limit, the volume is precise. So that's the idea that we've run with for pretty much all of our integration, and all we're doing here is we're extending it into 2 dimensions, and we're constructing a limiting process based on the volume of these prisms. Okay, let's look just a little bit closer at how this works through an example here. So, and this won't be how we solve these problems in practice, but this will be kind of a working example to get a little more detail, a little bit closer to the problem. Okay, so say we want to approximate the volume of a solid lying between the paraboloid, and we'll write the equation here for the paraboloid. It's going to be 1 minus 1/2 x squared minus 1/2 y squared. Okay, so this is the function of that describes the surface, which creates this solid figure called a paraboloid. So we want to approximate the volume of the solid lying between this paraboloid and the square region, and we'll call it R in our construction, given by 0 less than or equal to x less than or equal to 1, and the same for y. Okay, so we've got some square region underneath this paraboloid. Okay, and so just kind of we're going to basically apply the previous technique, but we want to dive into a little more precisely, like how we might think of this if we were trying to work this out from scratch. So if you think about looking down on our grid, it's a 1-by-1 grid, right? And let's go ahead and say we're going to make our partition we're going to use a partition made up of squares whose edges have a length of like 1/4 of an inch. Okay, so if this is our y-axis, this is our x-axis, then this is the region we're interested in. This will be 1 and 1. Okay, and so this over here is, I guess we'll label the points. This would be 1, 0. Up here, this would be 1, 1. This over here would be 0, 1. And then, of course, you've got the origin here. All right, and so if this is 1 unit, then each of these is a 1/4, right? And so our partition would look like this. Right, it would be just this square region broken up into 16 different squares. Okay, and so the question then comes, how do you want to choose the height of your prisms? Like, what points do you want to use? Well, just for convenience, let's just use the center point from this grid. Okay, so let me redraw it here. Okay, so if we redraw that, basically what we're interested in is what are the coordinates of each of the centers. Right, those are the xi, yi's that we're interested in. All right, and so you can figure this out pretty easily. Over here you've got your 0, 0. All right, so what is this point here, for example? Well, this length is 1/4, so it's halfway through that, so it's an 1/8 over and an 1/8 up. So this would be the coordinate 1/8, 1/8. What about this one here? What is this coordinate? Well, it's 1, 2, 3, 4, 5, 6, 7/8 over and 1/8 up. Right, and so on, right? You could go on and on like this until you get them all. This one up here would be 7/8, 7/8. This one here would be 1/8 over, 7/8 up, right, and so on. Right, I don't want to, obviously not going to go through them all, but you get the idea of how you could pretty easily come up with what all of the coordinates are of interest. Now, what's the area of each of the bases of each of the squares here? Well, the area of each square it's 1/4 by 1/4, right? So it's 1/4 squared. So you get 1/16 for each of these, right? So the delta AI here is 1/16. Okay, and so what would the sum look like in the case of this particular function and this particular grid? Well, the volume would be approximately equal to the sum from I equals 1 up to 16, right? There's 16 squares. And it's going to be just kind of writing out it's going to be whatever the height of each of the prisms are times the base area of the prism. In this case, the base area is all the same. And so it's going to be equal to I equals 1 to 16. And then let's put the function in. It'll be 1 minus 1/2 x squared minus 1/2 y squared. You know, and so these would have to be, I should put subscripts I here, right? So it depends on the I. Times 1 over 16. Right, so this is a big old mess. Let's write out the first term and the last term just so we know what we would plug in here. So this would be equal to 1 minus 1/2. Now the first dot we'll say is this guy, 1/8, 1/8. So it'd be 1/8 squared minus 1/2 times 1/8 squared times 1 over 16. That's the first term. Right, just plugging 1/8 in for xi, 1/8 in for yi, and that's what you get. And you could do the same thing for the second term and the 15th term, and then the 16th term here would just be the last one, right? It'd be the 7/8, this guy up here. So you go like this. Okay, so it'd be 1 minus 1/2 times 7/8 squared minus 1/2 times 7/8 squared times 1 over 16, right? So you go through this whole thing. Now, obviously, you wouldn't want to calculate this by hand. So I did do this calculation just using this grid. I kind of did it. I automated it, just pulled out a spreadsheet or something. And I got something like 0.067. Okay. Okay, so that would be an estimate of this volume. Okay. Now, it turns out that the true volume is 2/3. Okay, so that's 0.0666, etc. Right? However, you know, to infinity. Right, so just write it like that. There's no 7 there. And so the discrepancy there between the two is due to the fact that the partition isn't precisely. We didn't take the limit, right? We just stopped at, you know, a partition of fineness 16, and that was good enough, right? But if you kept going and going, then obviously the precision would increase, and we would eventually arrive at the precise volume of 2/3. Okay, so this is how the double integral works. Let's define it formally. And then we'll get into some more practical consideration about how to actually calculate things like this and some of the properties. So let's start with a formal definition here. So if f is defined on a closed and bounded region R, okay, and this region's in the XY plane, then the double integral of f over R, okay, is given by, okay, and here's the notation. So again, it's just two integral signs, and usually that's, if it's a double integral over a region, you can just denote it like this, right? So it's going to be f of xy dA, a meaning area, okay, and that's equal to the limit. Right, now here's kind of where it comes from. This is the limit as the norm of the partition, as we just defined, goes to 0 of the sum from I equals 1 up to n of f of xi yi times delta ai, right? So these are all the quantities we just talked through, right? So the limit as the norm of the partition goes to 0 of the sum from I equals 1 up to n. N will obviously increase as the partition decreases. As the partition norm goes to 0, the number of squares required to partition the region increases to infinity, and the sum turns into this integral. Okay, so this is what the definition of the double integral of f over r is. Right, and this is, of course, all provided that the limit exists naturally. If you can't take that, if that limit doesn't exist, then the double integral can't be calculated. Okay, it does not exist. And so, as we've seen, this double integral has as kind of its basis the use case of finding the volume of a 3D region kind of under a surface and above the xy plane. Okay. This integral has the use case of finding the volume between f and the xy plane. Okay, perfect. All right, so that's the definition of the double integral. And I mean, as I, we kind of talked it through, sort of like where the idea for this comes from is sort of like was all prefaced here, right? So we kind of talked through how it's set up and then kind of, recapitulated everything in this more concise definition. Okay, so hopefully that's clear. It's relatively straightforward. Where double integrals become I think intuitively they're fairly straightforward, but they can become very challenging when we get into actually calculating some of them. And we'll get into that in a second. Before we do that, we're going to run the obligatory properties theorem past everybody here. So properties of double integrals, right? And you got to do these. A lot of this will come up as we're trying to do some of the evaluations. So let f and g be continuous over a closed interval. Bounded plane over a closed, I didn't mean to write interval, closed and bounded region R in the plane. Sorry about that. Let f and g be continuous over a closed and bounded region R in the plane. And let's let c be a real number constant. Okay. All right, so then the following is true of the double integral. So the double integral of a constant times a function is just, you can pull the constant out. Okay, so that's nice. Basic. I mean, a lot of these are going to be kind of standard. The sum or difference of two functions inside the double integral can be broken apart, right? So if I've got f, I'm going to kind of abbreviate here, f plus or minus g, that's going to be equal to the integral of f plus or minus the integral of g. Okay, now again, I'm abbreviating, so this is all the same notation. I'm just kind of cutting it down a little bit. Right, and the double integral of f is going to be a positive quantity if f is a positive function. Okay, so if f is greater than or equal to 0, then the double integral over f. And of course, this is all in the region, right? Right, this is assuming that f is positive on R. Okay, and let's see inequalities properties will hold as well. So the double integral of f is going to be greater than or equal to the double integral of g if f is greater than or equal to g. Okay, so kind of standard. You would expect that. And then this last one says the following, and I'll pull in the full notation for this. Right, so the double integral of f on a region R is equal to the double integral of f on the region R1 plus the double integral of f on a region R2 if the sum of the two subregions is equal to the overall region. Another way to say that would be if R is equal to R1 or R2 and the intersection of these two is empty. Right, so basically if R1 and R2 partition R down, then you can break the integral up over those two separate subregions, add them together, and you get the full region. Okay, so again, these are all very common sensey. I mean, if you think about what the double integral is telling you, it's giving you a volume. These are all hopefully very intuitive, right? If you break if you break the base of a volume into two pieces and you add the two separate volumes together, you ought to get the whole volume. So hopefully very straightforward. Okay, so that's those are some of the properties, and again, we'll need some of that in some of the examples to come. So that's sort of why I want to make a point of bringing these up. Okay, so now the question comes up. Obviously, I mean, we kind of maybe get a sense for what a double integral is now. It's a volume. How do we evaluate them? How do we evaluate double integrals? Okay, and so normally the first step in evaluating a double integral is to rewrite it as an iterated integral. So that's the first step. Now, there may be some exceptions to this, but in general, this is what you want to do. Right? So in general, we'll want to rewrite our iterated integral, our double integral, as an iterated integral, hence the necessity of doing 4.1 first before we got into this. Okay, and so let's do an example, kind of walk through. This will be kind of a sort of a slow build example. This isn't a run for the finish line kind of example. Let's consider the solid region bounded by the plane, and the plane, so bounded by the plane z equals 2 minus x minus 2y. So this is a plane in 3D space, right? It's not a coordinate plane, but we're going to consider the solid region bounded by this plane and the three coordinate planes. Don't worry, I'm going to draw a picture in a second. And the three coordinate planes. Okay, so this is the setup. Let me draw a picture of what this looks like. Okay, and this is a relatively easy example to think through. So up here we're going to have the point 0, 0, 2 on the z-axis. Over here we're going to have the point 0, 1, 0 on the y-axis. And then on the x-axis we're going to have this point 2, 0, 0. Okay, and the plane is going to intersect these three axes at these points, right? And so you can imagine it's going to look like this. Now the area that the volume that we're interested in is, so you've got this plane here that's intersecting the three axes, and it's going to create this sort of tetrahedron-y sort of shape. Okay, and so we're interested in the volume that falls between the xz plane, the yz plane, the xy plane, and this arbitrary plane right in the middle here. Okay, so that's what we're up to. Okay, And so the way we're going to do this, and again, this can be defined as a double integral, right? And so what we're going to talk through is how to actually convert these double integrals into iterated integrals and how to actually calculate them, right? And so the way we want to think about it, and again, I have to draw another picture here, unfortunately. And so I'll try to do this well. I kind of looked at this up beforehand. So we'll go up. So again, you've got your z-axis up here, you've got your y-axis here, and then you've got your x-axis down here, right? And then here are the points that I just indicated, right? So you've got the intersection here and here and here. Right, now the way we're going to think about it is we're going to drop a vertical cross section onto this three-dimensional figure, and we're going to drop the vertical cross section so that it's parallel to the YZ axis. So namely this axis, or sorry, the YZ plane. Okay, and so you can imagine what that would look like. It would kind of, for example, you might have one of them, a slice right here. Okay, so you can kind of think of this slice right here. Right, and you would have, you know, an infinite variety of these as you move from the front of the region to the back of the region. The back of the region would just be this guy here. The three-dimensional slice would be this piece here, right? And as you bring it forward, it gets smaller and smaller until it's a tiny point. Okay, so that's a starting point. So think of a vertical cross section taken parallel to the YZ plane. Okay, so this is a triangular region. It's a triangular region. And this triangular region is going to have a base length right down here. And it's going to have a height. Now the height is going to be basically dictated by this edge here, right? Because you can see how it's set up. The height is always going to be this back wall of it. Okay. So you're going to have a base and you're going to have a height. Okay. Now, what is the base and the height of this guy? I mean, we're talking triangles. We're going to have to build up an area. So what we're interested in is the area of this triangular slice of the region, and that's going to be 1/2 base times height. So what is the base and what is the height? All right, so we'll start with kind of think of the base. Right, so the base you can think of is it's going to be this distance right here, right? And that distance you can think of as being based on the line y equals, so this line right here is going to tell you how long that distance is. And that line right there is, so it's based on y equals negative 1/2 x plus 1, right? So this is the positive x-axis right here. It's the positive y-axis. This is the line negative 1/2 x plus 1. Right, and so the base here, the base is going to be equal to, let's rewrite this in a slightly nicer way, it's going to be equal to negative x over 2 plus 1, which is negative x plus 2 over 2. And so we'll say the base is equal to 2 minus x over 2. Okay, so that's this part. Okay, now what about that height? What about the height? Well, we're going to use a similar argument for the height. The height is based on this line right here, right, which is in the xz plane, right? And so the height is based on this line right here, which is in the xz plane. Okay, so the height is based on What is that line? Well, remember this goes through 0, 0, 2, right? So the intercept there is 2 on the z-axis. And the slope is, and this is 2 here as well, so the slope is just -1. So it's based on the line z equals -x plus 2. Okay, so the height is just z equals 2 minus x. Right, and so we can write that in here. 2 minus x. Okay, that's that part. Okay, and so what is the area of this slice of this three-dimensional region? The area, which is a function of x, is going to be equal to 1/2 base times height, which is 1/2, and the base is 2 minus x over 2. The height is 2 minus x, and so this is going to be the area, and so we can see that that's equal to 2 minus x squared over 4. Okay. Okay. And so this gets us the cross-section, the area of the cross-section, and so then the volume of, this is, if we think about going back to calculus 2, the volume of a solid whose cross-section is known is straightforward, right? So the volume of a solid whose cross-section is known is taken from, basically from calculus 2. It's going to be equal to the integral from a up to b, so a up to b, of the area as a function of x dx. Right, so in our case, this is going to go from 0 to 2. Right, so you can think of it as 0 up to 2. You can kind of come, you can come from here forward or from here backwards. It doesn't matter. You should go from 0 up to 2. It's just the way that this looks, the way that this is drawn, it looks like you're coming in kind of the reverse direction. But this is the positive x-axis here. So from 0 up to 2, and then the a of x here we just calculated, we figured out was 2 minus x squared over 4. Okay, and so this is what the integral would look like. And so can we calculate this? Yes, we can. All right, this is a simple integral to calculate, and what if you do that, you'll get 2 minus x to the third power over 12. And this is going to go from 0 up to 2. Okay, and so we could plug all of these things in. And what do we get? We get, do it up here, negative. So you plug in a 2 first, so it'd be 2 minus 2 cubed over 12 minus, and then it's negative 2 minus 0 cubed over 12. Okay, and what do you get there? You get, so this is 0, and then it's minus, and then this would be a 2 cubed would be 8, so negative 8 over 12. Okay, so you get 8 over 12, or otherwise known as 2/3. Okay, so the volume here would be precisely 2/3. Okay, and so this is, again, what we're trying to do here is we're starting with the idea of a problem where you would use a double integral, and we're just sort of roughing it out. Right, we built up a formula for the area of these cross sections, right? And this is the formula we got. And then we said, hey, if we know the cross section of a figure, we can easily calculate the volume using Calc 2 machinery, and that's what we've done here. Okay, now the process that we just outlined here works irregardless as to how a of x is determined, right? So this process works without regard to where a of x comes from. Right, so specifically when I say that the volume is equal to the integral from a to b of a of x dx, this process works. It doesn't matter where we get the a of x, right? And so what we want to do is, we want to, what we're kind of headed towards is finding this a of x using integrals, an integration itself, and then you would have an integral within an integral, and you would get your iterated integral. So that's the idea, right? So in particular, we could find a of x by integration. Okay, so that's kind of what I'm saying there. Okay, so specifically, if we think about looking down on the cross section that we just described, okay, and we think about having representative rectangles running in this orientation. So this would be y equals 0 over here. Over here, you'd have y equals 2 minus x over 2. Okay, and what is this line here? Well, this line is just z. This is the function itself. Z. This is the surface. Right. This is z equals 2 minus x minus 2y. Right. And we're looking down on a triangular cross section. Okay. And so, can we figure out the area of this region, using the coordinates that we have here? Definitely, right? What would we do? We'd say, well, a of x is equal to the integral from 0 up to 2 of this guy here, 2 minus x minus 2y dy. Oh, sorry, not 2. 2 minus x over 2. Where I'm going from here up to here, right? And I'm integrating this minus 0, right? So this is the 0 line. Okay, so that's where that comes from, right? So 0 up to 2 minus x over 2. And what happens when I do that? Well, the integral I get is, this will be 2y minus xy minus y squared, right? So that you get 2y squared over 2 there specifically. And that's going to go from 0 up to 2 minus x over 2. Okay, and we can simplify this a little bit. Let's write 2 minus x times y minus y squared from 0 up to 2 minus x over 2. And what do we get? Well, we get 2 minus x times 2 minus x over 2 minus 2 minus x over 2 squared, and then minus everything is 0. So this is the upper one, and then the lower one is all zeros. Okay, so minus 0 minus 0. Okay, and so then we just have to kind of clean this up here. So we get, this will be 2 minus x squared over 2 minus 2 minus x squared over 4. And so get the common denominator, you get 2 times 2 minus x squared minus 2 minus x squared over 4. And so I think you can see the answer is the same as what we got before when we kind of reasoned it out geometrically. Okay, so for the area function, right? So the area function is the same, right? So previously, we had come up with this area function, if you recall, right? The height was based on this, so the area function was 1/2 base times height, and so you got this. And now we're saying with an integral, you could do this just as well. Okay, so then the idea here is for the iterated integrals to combine these previous two results. So combine this result, i.e. being able to find the area using an integral, so combine this result, i.e. finding the area using an integral, with the previous result where we found the volume i.e. finding a volume by integrating over an area. Function. Okay, sorry about that. So combine this result with the previous result and you get what we're after. What do we get? Well, what we get is this iterated integral, right? The integral from 0 up to 2, and then from 0 to 2 minus x over 2, and then the function itself, 2 minus x minus 2y, and then dy dx. This is equal to the volume. Right, so obviously this inside one is the one we just did. Right, so we know when we integrate this inside integral, we're going to get this. And then when we integrate this with respect to x from 0 up to 2, we're going to get 2/3. Okay. And so that's the idea. That's the basic gist of what we want to be able to do with these double integrals. Using via iterated integrals, we want to be able to calculate this. Now, the way you should kind of think about this, how is the volume accomplished in this way? The volume is accomplished by basically two sweeping motions. Okay, let me try to draw a picture. The first sweeping motion is, okay, so you've got your x, y, z's here, right? And here's your region of interest. Remember, this is the plane. And so the first sweeping motion is sweeping out a cross section. Right, so you sweep out the area of one of the cross sections. So you integrate with respect to y to get the area of the cross section. Okay, so that's the first sweeping motion. And then secondarily, what do? Well, you come back through once you have the area of the cross section and you sweep out the volume. Right, so if this is my same shape, motion 1 sweeps out the area of the cross section. So I get this whole area of this back panel. You can think of this as the back panel of this guy. And then what am I going to do? Well, I'm going to sweep it forward. I'm going to sweep those cross sections forward. Just going to drag it forward and integrate in the other direction. So you then integrate with respect to x to get the volume of the entire solid. Okay, so that's the idea. It's like it's double sweeping out of the volume. First you sweep out the area of the cross section, then you take the area of the cross section, you sweep out the entire volume by basically going in the other direction. Right, so this double integral idea, that's how it works. That is the basic setup. Okay. All right. Very good. I'm going to go ahead and pause the video here because it's going to become long. I've got a bunch of examples to do. So we'll pause the video here, and then we'll come back in part B to do some examples. Okay. See you in a second.